Good morning, everyone. Our demonstration today is a quick one. How to correct the drift on microscopy images that are taken over time. So the project that this is for is one where we're studying the growth of these voids in a material. What's happening here on the material science level is we're irradiating a sample inside of a transmission electron microscope. So what you're seeing are little voids forming as a result of the radiation destroying the structure at the atomic scale. If you look at the scale bar, that's 100 nanometers across. An atom is kind of roughly a quarter nanometer in size, so it's about, each of those voids is maybe 40 to 80 atoms across, which is mind-blowing, but not the point of the lecture today. What we're going to talk about instead is how we correct for the drift that you're observing in these microscopy images over time. And that drift is natural. The material, as we mentioned, is getting rapidly deformed because of the effect of the radiation, among other things. So let's talk about how to correct that. If we go to Jupyter, we're going to show how we can take images and use a cross-correlation analysis to be able to correct that drift. So cross-correlation is a signal that you can compute that tells you how well two different signals, in our case images, overlap with each other as a function of certain offsets. So what you're seeing here is that this cross-correlation signal on the right is highest when I offset the sine and cosines by about a quarter period, which we know is what will make the sine and cosine line up. So let's do that with images. So the problem at first is that computing this with images can be slow, especially when we use images that are high resolution microscopy images that each have 1 million pixels. So what we're going to do is use a technique based on Fourier transforms. I cannot explain the math to you, I'm sorry, but what we can see from this theorem down here is that I can compute, this is a cross correlation, between two images using a Fourier transform so long that as I reverse the second image. Fourier transforms are actually very quick to compute thanks to some other clever mathematics I don't know, and thanks to Stack Overflow you can find quickly how to compute them using SciPy's fast Fourier transform convolution operation. So let's go and do a quick demo of how that works. Let's see, let's restart and clear all outputs. So I'm going to load in a series of images. These are images that I've taken, and as in our video, I've computed the mask of where all those voids are located. Correlation is going to work best when we have images with fewer noise in them, and I'm removing all noise, that is everything except the drift in the voids that I care about. So let's pull two up. I'm pulling them far apart in the video to exacerbate the differences between them. And you can see between this first and second images, I can look at the patterns of these voids and note two things. It tends to drift to the left. See these two? They've moved to the left, and they've also moved down a little bit. So that's what I'm expecting to find. And I'm going to write a little function here, basically verbatim from that Stack Overflow, where I take two images, I reverse them. This is the Python shortcut for taking a list and going through it in reverse order. This says go from the beginning to the end, stepping by -1, which is the equivalent of going through in reverse. This computes a convolution signal, which we're going to go and open that in another window. I'll show you what the result is before finishing explaining it. Yeah, let's open this image in a new tab. Awesome. Come on, do what I need. All right, let's run it. I didn't rehearse this. All right, let's open you in a new tab. Perfect. So yeah, if you take a look here, here are my two images. See how there's that left and downwards drift. My convolution plot is going to give me that cross-correlation signal, and I need to pick out where the maximum of that signal is, which we can see is about here. The way you do that is you compute the location of the maximum using argmax. That's going to give me a position in the list, counting row-wise. It's going to be a single number, not a 2D coordinates, and I can convert it to a 2D coordinate using NumPy's unravel index, given that one-dimensional coordinate, and the shape of the array. I can then take that and I can compute, kind of given this peak location, where that is in reference to the center. I can see that it is, I'm taking the negative, it's slightly to the left, negative x, and down, positive y. And that gives me my offset. So what I'm seeing here on my plotting is that my images, if I do take them and I account for the drift, I'm using scikit image as a fine transform to compute the shifted image. That will give me it on the left. So we're going to take it and we're going to run it for the whole thing. We're going to go to the cooking show demo because this takes about an image. Let's go to the real-time defect analysis. This is up on GitHub, and I'll give you this link later. And yep, align images, and we'll see over time I can compute both the X and Y drift. And these vertical bars here are what I'm showing are where my experimentalist colleague knew he adjusted the microscope to counteract the drift. And you can see that those line up well to where my code is detecting the very large drifts. So everything seems to be working here. And this is going to take about a minute to run through. It does about 15 frames a second. So it's fast enough for me to do on an entire video. That's all for today. Hope this helps you become more familiar with the scientific Python landscape.